Hello, my name is Nikolaev Sergey. I'm head of Laboratory of New Materials for Infrared Photonics in Lebedev Physical Institute. I want to talk about semiconductor physics, and first of all, I start from history of semiconductors, physics and technology, and after that I discuss some basic concepts of semiconductor physics. Discovery of semiconductors is bound to name of Michael Faraday. He is noted that resistance of silver sulfide drops with temperature increases in opposite way that metal behaves. Also, semiconductors like silicon or germanium has conductivity somewhere between metals and insulators. And at the end of 19th century, new era of semiconductors investigation starts. First semiconductors device was crystal detector, and it was invented after Carl Brown discovery of rectification or asymmetric conductance in the metal semiconductor junction. But he can't find any application of this device, and only in 1890s Bose used this crystal detector to detect radio waves. In 1905, Pickard patented silicon crystal detector, and this device was widely used in radio receivers, for example, Marconi type 106. At this moment, there was a lot of phenomena discovered in semiconductors. For example, thermal electric effect discovered by Seebeck, photovoltaic effect. Also in 1906 was first observed electroluminescence from crystal detector. To explain all these phenomena, you need to construct semiconductor theory, and first step in this way was done by Felix Bloch. He developed theory of electron movement in crystal lattice or periodic potential. After that, Alan Wilson, Schottky and Mott was developed theory of band theory of conduction and models of potential barrier or metal semiconductor junction. These theories opened a way to construct new devices based on these principles. First of this device was semiconductor diode. It's a more practical way of crystal detector that purify applied voltage and conduct current only in one direction. PN junction diode was developed in Bell Lab in 1930s, 1940s, and after that, in several decades, other diode devices was constructed. For example, Zener diode or tunnel diode. Zener diode, for example, used to obtain constant voltage, and this diode works in opposite direction in breakdown region. And tunnel diode was invented by Leo Isaki, and interesting property of this diode is negative differential resistance in some voltage region. But the most important invention in semiconductor physics is the invention of point contact transistor. This invention was made by a group of physicists from Bell Lab, Shockley, Bardeen and Breton. They made first transistor in 1947. This invention is so important because transistor allows to amplify signals, and all other amplifiers was built on based on these devices. After point contact transistor was invented, bipolar junction transistor was invented too in a couple of years. These devices was rather big and not so convenient to use, but in a decade, in 1960, modern metal oxide semiconductor field effect transistor was invented. This transistor scheme is now used in all the electronics around the world. Next step to obtain our modern technology of semiconductors was made by Kilby and Noyce. They independently invented integrated circuit that allows to put several semiconductor transistors and other elements on one substrate. Other important region of semiconductor physics is bound to electroluminescence. First observation of electroluminescence was made in 1906, but the creation of light-emitting diode was reported in 1947 by Oleg Losev, a Russian inventor. But he can't find any application for this invention, and only in 1961, infrared light emission from germanium arsenide tunnel diode was discovered and find application in signal transition. After that, this region of semiconductor physics connected with light emission was developed, and in 1993, high brightness blue LED was demonstrated by Shuji Nakamura, and group of Japan physics was win Nobel Prize for this invention. All our light emitting diodes that we use nowadays for indoor luminescence was made by this technology. Development of integrated circuit technology leads us to construction of microprocessors. First microprocessor was introduced by Intel in 1971 and obtained about 5,000 of transistors. Nowadays, our commercial CPUs have billions of transistors, and all our information vault around us now connects with semiconductor devices. But what properties of semiconductors leads to this huge industry? First of all, most of semiconductors are crystalline. What that means? That means that atoms in this solid state has periodic arrangement. So then you take one part of this crystal and translate to specific vector, you obtain the same crystal structure. Small part of crystal structure that can produce all crystal by translating on lattice vectors is unit cell. Most common lattice systems is cubic systems. For example, simple cubic where atoms appear on vertices of cube. Body-centered lattice system where we add atom in the center of the cube, and face-centered cubic system with 6 additional atoms on the faces of the cube. If you take 2 face-centered lattice crystalline system and put together, you can obtain silicon crystal structure. It's named diamond cubic crystal structure. You can see that silicon atoms has connection with 4 neighbors, and in future we will show this crystalline structure in more simple cartoon image like shown in this picture on the left. To understand physics of crystalline silicon, let's start from electronic structure of a single silicon atom. Silicon has 14 electrons, but only 4 of them can form chemical bonds. And you can imagine that silicon form 4 bonds by 4 electrons from each atom. Band formation, when you brought large number of silicon atoms to form crystal shown on the picture. Then silicon atoms are far apart. The eigenstate is atomic orbitals. When silicon atoms come close to each other, atomic orbitals hybridize to molecule orbitals. And as far as there are a lot of silicon atoms in this crystal, there are a large amount of these molecule orbitals. So energy distance between this orbital is very small, and you can talk about continuous band of state in some region of energy. For a certain distance between silicon atoms in silicon crystal, these states separated on 2 bands. One is fully occupied and other is empty. Occupied band is named valence band, and empty band is conduction band. Between these bands there is no electron states, so this part is named band gap. Top of the valence band is noted as EV, and bottom of conduction band is noted as EC. Band gap is EG. Now we can talk about difference between insulators, semiconductors, and metals. In semiconductors, band gap between valence band and conduction band is about 1 electron volt, but in insulators, this band gap is much higher and have value about 3 or more electron volts. In metals, there is no band gap, and band is only partially occupied. So you can think that electrons on silicon atoms form covalent bonds with 4 neighbor atoms, and these electrons fully occupy valence band, but there is no free electron in the conduction band. This picture is correct at a low temperature, about absolute 0 temperature. What happened if we warm up crystalline silicon to room temperature? There was enough thermal energy of silicon atoms movement to break some covalent bonds, and electrons from valence band moves to conduction band. These free electrons in conduction band and holes in valence band can carry charge in semiconductor crystals. To understand why these free electrons is important to understand conductivity of semiconductors, I remind you some basic formulas of resistivity. First of all, resistance of bulk crystal you can explain in terms of resistivity and geometric sizes of this crystal. Conductivity is reciprocal resistivity, and you can rewrite Ohm's law in terms of current density and resistivity, or current density and conductivity and electric field. From microscopic point of view, current density is equals to product of particle density, their charge, and drift velocity. So conductivity you can explain as production of particle density, their charge, and mobility. So the larger particle density is in our crystal, the larger conductivity in our material. Let's calculate concentration of free electrons and holes in intrinsic semiconductor. Intrinsic semiconductor is semiconductor without any impurities in this crystal. To describe this system, you need to use Fermi distribution function that Fe, but in our case we can rewrite this distribution function in more simple way and use Maxwell-Boltzmann distribution to describe occupation of electron in conduction band and holes in valence band. You can obtain electron and hole concentration N and P as function of Fermi energy and temperature of crystal. N sub C and N sub V is effective density of states of conduction and valence band respectively. If you multiply N and P, you obtain some function that don't depend on Fermi energy at all. If you take into account that N and P is equal in intrinsic semiconductor, then you obtain the concentration of free carriers in intrinsic semiconductor as square root from NC and V and exponential decay e to the power of minus Eg over 2 kT, where K is Boltzmann constant and T is temperature. So you can see that free electron concentration increases with temperature increase and increases with drops of Eg. So in insulators with Eg about 5 or more electron volts, there is very low concentration of free charges carriers. And in semiconductors, like in silicon, this concentration is much higher. Also, from the formulas of electron and holes concentration, you can derive position of Fermi energy, and it placed in between of conduction and valence band at low temperatures. But what changes if you put some impurities in your semiconductors? These semiconductors is named doped semiconductors or extrinsic semiconductors. If you replace some silicon atoms by atoms from 5 group of periodic table, for example, antimony, there was some additional electron in crystal lattice, and it electron only weakly bounded to antimony atom. So with temperature increase, these electrons became a free electron in conduction band. If you replace some silicon atoms by atoms from third group of periodic table, for example boron, these atoms has only 3 valence electrons, so one of the bonds have no electron. Electrons from nearby electrons can hop to this hole near boron atom, and such movement of hole you can explain as movement of positive particle through crystal. Let's calculate electronic concentration in n-type doped semiconductor with additional electrons and donors in this crystal. You can separately calculate concentration of electrons in different energetic or temperature region. At low temperature, when thermal energy lower than energy separation between donor level and conduction band, the concentration of free electron you can explain the same way as for intrinsic semiconductor, but with very low energy gap, delta D. But if you heat your crystal and your temperature is now larger than this bound energy of electron to donor atom, then all of these donor atoms are ionized, and concentration of electron N is equal to Nd, which is donor concentration. In this thermal region, there is saturation of electron concentration in crystal, and when intrinsic concentration is bigger than donor concentration, this silicon crystal behaves like intrinsic semiconductor. You can see this behavior on this graphic. Here, electron concentration depends on reciprocal temperature, and at low temperature there is freeze-out range, and after temperature increase you obtain saturation range and intrinsic region. Let's discuss simple physics of p-n junction. If you put p and n type semiconductors in contact, free electrons and holes drifted to another region, and in between p and n type semiconductors appears depletion region without free electrons and holes. This region form energy step between semiconductors that prevent charge carriers mobility and current from structure. But if you apply positive voltage to p-type range of this diode, this energetic step drops, and electron and holes can freely goes through structure. If you apply a negative voltage to p part of this diode, the step increases and no current you observed. This behavior you can see on p-n junction dependence of electric current on volts applied to structure. At the forward voltage, current through diode increased rapidly, but for backward direction there is no significant current before breakdown of device. Other way of excitation of electron from valence band to conduction band is absorption of electromagnetic waves or photons. If energy of photon is bigger than band gap, then this absorption can move electron from valence band to conduction band. But if energy is not enough, there is no absorption and no electron excitation. After this excitation, electrons and holes rapidly relaxate to bottom of conduction band and top of the valence band. Radiative recombination of electron and hole in semiconductors is luminescence. These processes is responsible for light emission diodes or semiconductor lasers operation. Also, you can see the process of absorption of light in semiconductors. On this picture, here is a spectrum of absorption, several semiconductors. You can see step on the band gap energy for each semiconductor. We talk now about bulk semiconductors, but new idea was invented by Alferov and Kramer is to use semiconductor heterostructures. Then you combine different materials in one crystal structure. First of all, you can obtain localization of electron and hole states in semiconductor with narrower band gap. but if you change the thickness of this layer of narrow bandgap semiconductor, you can obtain change of electron and hole energy that localized in this layer. You can see some similarity between this localized electron and hole states with standing waves in Fabry-Perot cavity or strings on musical instruments. For example, on guitar, the tone is higher than string is shorter, so the energy of electrons and holes also decreasing the thickness of this semiconductor layer. But new phenomena you can observe if you take not one quantum well, but several quantum wells. Leo Isaki won Nobel Prize for his invention of tunneling phenomena in semiconductors. If semiconductor barrier between quantum wells is thin, the states of electrons and holes in these quantum wells interact with each other, and in full analog with crystal structure, one energy level transforms to mini gap, and each electron and hole state produce own hole and electron mini bands. This structure is named superlattices, and it provides to produce semiconductors with artificial properties that you can't achieve by bulk semiconductor. Other way to localize electron holes is spherical nanoparticles, and in agreement with our previous explanation, changes of diameter of nanoparticles leads to change of spectrum of luminescence of these nanoparticles. Also, you can control not only core material of this particle, but also a shell that confine electron and hole, and obtain different electron and hole distribution in these quantum dots. After graphene discovery by Game and Novoselov, the field of layered semiconductors starts to actively develop. The main idea of layered semiconductor physics is to construct heterostructures from different materials with atomically thin layers. And also you can use not only semiconductor layers, but insulators and conductors like graphene. Here you can see constructed junction field effect transistor that constructed with molybdenum diselenide and molybdenum ditelluride layers. This junction field transistor can work both in P and N channel and works at low gate voltage. Layered semiconductors also give us opportunity to construct photodetectors. Here, MOS2 phototransistor demonstrated with high detectivity and photogain. Then you put two flakes of layered semiconductors on each other, you can produce periodic Moir pattern that depends on the angle between these sheets. This periodic potential is similar to crystal periodic structure, so you can control semiconductor properties not only by materials but also by angle between these layers. New material that actively investigated in this decade is perovskites. These materials has organic or non-organic cation A. Perovskite nanocrystals are efficient light source. Also, high photovoltaic response allows us to use perovskites as solar cells, and in tandem cell with silicon solar cell, they achieve 34% of efficiency. New interesting idea in perovskite semiconductor physics is to synthesize organic nanocrystals with organic separation layer. Combination of different concentration of bulky organic cation and small organic cation allows to achieve 1, 2, 3, or 4 layers substructure in perovskite nanocrystals. So this is new material for two-dimensional physics. In summary, I want to talk that the study of semiconductors spent almost 2 centuries, evolving from basic experiment to huge industry. Key technology development include the transition from early diodes to advanced transistors or integrated circuits. Band theory provides a fundamental understanding of semiconductor physics, explaining crucial phenomena such as temperature-dependent conductivity and mechanisms of light absorption and emission. Modern semiconductor physics placed great importance of low-dimensional structures and metamaterials, which give advancement in various applications. These include superlattices, quantum dots, two-dimensional materials, and perovskites. Thank you.